A follow-on video from the last one I did on two-dimensional SUVAT. So the last video I looked at slopes and I looked at projectiles in terms of the general equations, and in this particular video I'm going to look at some specific examples of how we apply SUVAT in two perpendicular dimensions, again with slopes and projectiles, and we'll look at how we can calculate some different properties of projectiles. So we'll look at how we get maximum height, flight time, range, and final velocity. Okay, so we've got a 5 kilogram mass sliding down a 30-degree slope, and we want to express its acceleration as a vector. So the first thing I do is I draw a diagram like we can see on the left, and then I would decide which two perpendicular directions I'm going to be using. So with a slope, we always use a direction parallel to the slope called the I direction, and a component perpendicular to the slope I called J. So we're going to resolve the weight force into those two directions. So you can see from the diagram, we've got the component in the I direction is W sine theta, which is why it's on the top line of the vector. And the component in the J direction we can see is W cosine theta, but it's in the minus J direction, so it's minus W cosine theta. So we can express the weight force in vector form. Now what we can do is, using that, we can express the acceleration in vector form, because if we have the force divided by the mass, we get the acceleration. And that's where we get this G sine 30 from. So we take mg sine 30, we divide by the mass, and we get G sine 30. Sine of 30 is a half, so we can see the top line becomes 0.5 G. The rather odd thing we can see here is, why has the minus mg cosine theta disappeared? Well, that's because it's not only the weight force acting on the object, we've also got a reaction force which is acting perpendicular to the contact surface. And if we think about an object sliding down a slope, we know that that object isn't going to jump off the surface of the slope, or it's not going to dig its way into the slope. So intuitively, we know the component of the acceleration in the J direction is 0 there. And so then what this allows us to do is figure out actually what the reaction force is. So reaction force we can see has just appeared on the diagram. I've labeled it R. Reaction forces always act perpendicular to contact surfaces, which is in the J direction there. It would have no component in the I direction, which is why I didn't have to factor it into the acceleration vector. So if we actually want to figure out what the reaction force vector is, we've got what the weight force vector is. We've got it there, and we know what the resultant force vector is. You can see it here. We've just taken the acceleration and we've multiplied it by m. So what we should find is that W plus R should give us the resultant force, because we know resultant force is when we combine all the other forces together to give one force. So F is W plus R, so R would be F minus W. And when we actually do that, we end up with the vector at the end, 0 over mg cos theta, which we can see is essentially the opposite of the perpendicular component of weight force. So the perpendicular component of weight force was minus W cosine theta, so R must be plus W cosine theta, so they cancel out, leaving you 0. So that should be fairly intuitive there. Okay, so we've got the reaction force now on there. We calculated what it is. Let's have a think about how we can get some other equations to explain the motion of this object. So we've got the same object, but now what we're looking to do is express its velocity in vector form as a function of time. And we're going to use its initial speed of 2 meters per second. So we've got the acceleration vector already. The next thing is to turn the initial velocity into vector form. Again, we construct this by actually thinking about in reality. So objects slide parallel to the slope. So we know when it says its initial speed is 2 meters per second, we know that means it's going at 2 meters per second down parallel to the slope in the I direction. So we get the vector for the initial velocity is 2 over 0. Using v equals u plus at, then we can get a vector for the final velocity. Again, we know it's going to still be moving parallel to the slope, so we know it's going to be v over 0, and then we've just put u plus a t. So that's the equivalent in 2 dimensions. Okay, so then we can get an expression for the displacement as well. So again, using the same two vectors we started with, we're going to be using s equals ut plus half at squared. We know its displacement is going to be parallel to the slope. The slope forces it to be like that. So we get s over 0 is going to be ut plus half at squared, but in vector form. So we've got it in 2 dimensions. So a really good question at this point is, okay, so why have we resolved parallel and perpendicular slope? Because in most situations, we tend to resolve into vertical and horizontal directions, or x and y directions. Why is it changed for a slope? Well, the key is what you can see along the bottom line of our displacement equation there. We can see that resolving in these two directions, we end up with zeros all the way across the bottom, which makes it really easy to deal with. So let's have a look at how this would work or wouldn't work if we tried to resolve in vertical and horizontal directions instead. So first off, we can express the weight force in vector form. So we've got our I and j directions this time in horizontal and vertical. And so we get the weight force as 0 because it has no component in the horizontal direction, over minus mg because it's downwards. Reaction force, we would need to split into 2 components there. So our cosine theta would be in the vertical upward direction. Our sine theta would be to the left in the horizontal direction, so that's plus. And to get the resultant force, we'd have to add those 2 together. So that's what I've done. And then to get acceleration, we'd have to divide by the mass. Mass is a scalar, so it doesn't have a vector format. So we can just do 1 over m. And we end up with an equation we actually can't really do anything with because we don't know what r is. We've ended up with an equation we can't deal with because it's in both top and bottom lines there. So this is why we don't resolve to horizontal and vertical directions, because it gives us a horrible complicated equation, whereas if we do parallel and perpendicular, we get a nice line full of zeros, which makes it easy to deal with. Okay, so that's with slopes. Let's have a look at projectiles as well. So with projectiles, we do resolve horizontally and vertically. And the reason we do that is because we end up like we did just now with a whole line full of zeros, because we know the component of the acceleration in the horizontal direction is 0, which is very useful to us. And the way we assume that is by saying air resistance is 0. So we're going to ignore the effect of any air resistance on the projectile, which allows us to say the component of acceleration in the horizontal direction is 0. So in this situation, we've got an object that's 10 meters up in the air or has an altitude of 10 meters. It's fired at 20 meters per second at 60 degrees horizontal. And in this scenario, we want to get its maximum height. So an object in one-dimensional motion reaches maximum height when v is 0. So in two-dimensional motion, it's a little bit complicated than that, but not much. It reaches its maximum height when the vertical component of velocity becomes 0, because that's the component that gravity acts on. So if we use v squared equals u squared plus 2as, we don't need this in its two-dimensional vector form because we know a is 0 in the horizontal direction. So we're going to look just in the vertical direction. We're going to put in the vertical component of velocity, which is 20 sine 60. And then we're going to then calculate how much the object will have been displaced when v is 0. So 1.89 meters, but it started at a height of 10 meters. So that means the maximum height is 11.89 or 12 meters to 2 significant figures there. So we can get maximum height without even thinking about the horizontal direction, which is really useful to us. We only look at the vertical direction. Next thing we're going to do is calculating the flight time, or the time from firing to just before it hits the ground. So it's going to hit the ground when its vertical displacement is minus 10, because it starts 10 meters up in the air. It'll land when it's at 0, so it's displaced downwards by minus 10. So again, we're going to only be looking at the vertical components here to determine flight time. So we've ignored the whole horizontal direction, so all of these are in the vertical direction. So we end up with this quadratic equation once I've moved a few things around. So you need to solve this using a quadratic formula, which you'll have learned for GCSE or lower down maths, depending on what country you're in. Or if you're like me, you use Wolfram Alpha to solve this for you. We're not in an exam, so we might as well use a very effective and speedy method. Plug those numbers in, and we end up with two answers because it's a quadratic equation, so there are two solutions to this. So we end up with t is minus 0.51 or 4.0 seconds. So I'm going to eliminate that one right now. Time can never be negative. Time is always moving forward. Time is always a positive number. So although there are two solutions, this one makes no sense at all. So we get rid of it, and it's going to hit the ground after 4 seconds. So that's flight time. Another thing you might be asked is to calculate the range of the object, which is the horizontal distance it travels before hitting the ground. So just like in the previous ones, we've ignored horizontal components and only focus on the vertical ones. In this one, we only focus on the horizontal ones. We don't really care about the vertical ones. So in the previous question, we figured out what flight time was. We know what the initial velocity is in the horizontal direction, which doesn't change at all because acceleration is 0. So we just end up with this expression here, and we can get that the range is 40 meters. So if this is some sort of cannon, it means you can hit stuff 40 meters away from this setup. So that's range. So the last thing we're asked to work out with a projectile is what its final velocity is. So this time we have to look at two different directions to get the overall velocity. So we can't just focus on one or the other. But in the horizontal direction, the velocity is never going to change. So if we know what it is to start with, we know what it is going to be to finish up with. So we don't need to do too much there. In the vertical direction, we have to do a little bit more complicated because we need to figure out the velocity after it's gone up and come all the way back down again and is now 10 meters below its starting position. So we put in s is minus 10 into this equation here. We put u is 20 sine 60. That's the vertical component of the initial velocity. And I've left them as squares because we're going to be using Pythagoras in a second. So there was no point square rooting them at this point. So we've got the vertical component squared is like 496 something or other, but the horizontal squared is 100. So we add those together in square root would tell us what the magnitude of the final velocity is, which is 24 meters per second there. I realized that should be a -1 meters per second, not meters second there. At this point, you might be asked to find the direction of this, which could be done using simple trigonometry, but I showed you how to do that in the last video, so I'm not going to look at that now. So that concludes this video looking at some examples of how we might use SUVAT in 2 dimensions and why we resolve into the directions that we do. I hope you found that useful for learning on this topic. If you have any questions, please feel free to comment and ask me. I'll try and get back to you as soon as you can. But thank you very much for taking the time to watch this video.